Okay, everyone, this is going to be our next section here. 6.3 to 6.4, we're going to take a look at the relationship between the graph of the derivative and the graph of the function, which is the antiderivative. This is actually a really useful lesson for us, especially since the AP test really enjoys giving the graph of a derivative and then having us try to figure out what does the function whose antiderivative, what does that look like, or what attributes can we get from that. So we're going to get started with this right now. So let's go 6.3, 6.4. Okay, so each of the following graphs represents the derivative of a continuous function f of x. Sketch possible graph of f of x on the same set of axes. So we're going to have to talk about what certain parts of the graph of the derivative tell us about the function itself. So whenever we see the derivative equal to 0, and in this first graph, that is right here and here, that's going to be indicative of some kind of a relative min, relative max, or maybe even just a stationary point. So if I take a look over here at 0, 0, that's going to be a place where the derivative goes from negative to negative. So it's going to decrease, it's going to stop decreasing at x equals 0, and then it's just going to keep decreasing. Now, whenever you see a minimum or a maximum in the derivative graph, that's a place where you're going to have a change of concavity. So if you notice here, f prime is negative and then it stays negative, but the derivative of f prime, f double prime, goes from negative to positive. So right here, we're going to have a point of inflection. Okay. And the concavity is going to change from negative to positive. Also, at x equals 0, this is going to be another place where our concavity is going to change. Here, the derivative of f prime is positive, so we're concave up. And then here the derivative of f prime is negative, so we're concave down. So this is pretty much everything we're going to need to do. I also probably should mention that over here, we're going to have the function start increasing because that's going to be a relative. Well, the derivative, f prime, goes from negative to positive, so that's going to be a minimum. So let's pretend our minimum is right about here. Let's pretend, well, no, this is going to go through over here. So we're going to be decreasing, concave up, and then we're going to decrease, concave down. We're going to have a point of inflection, and then we're going to increase. So here is a graph of what number 1 would look like. Number 2, we're going to apply the same principles. This is a point of inflection right here. This right here, that's going to be a relative maximum. So let's draw our maximum up over here. This is going to be a minimum, right? Let's pretend our minimum is down over here. And this is going to be concave down and then concave up. So concave down, concave up. Concave down, and then concavity switch, and then concave up. There we go. Something like that. All right. Now, with question 3, all we know is that we are decreasing at the same rate here, and then we're increasing at the same rate here. So when the derivative is constant like that, you're looking at a diagonal line or something that's linear. Actually, we can tell a lot more. We know over here that the slope is negative 1. So we can just go ahead and draw ourselves something with a slope of negative 1. And then here, the slope is positive 1. Now, maybe they connect, maybe they don't connect. Let's pretend they don't connect. And as long as the slope is positive 1, this should be fine. Now, a lot of people might be drawing a V like this was an absolute value graph, and that would work as well. Remember that the graph of the derivative doesn't actually tell you the y coordinate. So anything would work like that. Question 4, we have, if this is the derivative, our function is always increasing, and it starts off with a slope of 0. So we start with a slope of 0, and then we eventually get to a slope of a very great positive slope. So I'm thinking something like this, which basically looks just like the derivative. Now over here, we start off with a slope of negative infinity, and we slowly get to a slope of 0. So I'm thinking that this is going to look like this. Now, one thing to know is that this graph for number 4 doesn't have any relative extrema because the graph of the derivative does not cross the x-axis anywhere. So that's how come you're not seeing me draw, for example, in question 2 where we had a relative maximum and a relative minimum. In number 4, there is no relative maximum and there is no relative minimum. 6 through 9 is a little bit of a matching game, which is nice. Okay, so this is a graph of f of x, and this is these are graphs of f prime of x, and we need to figure out which one matches with which. So if I take a look at this one, this graph is decreasing and then decreasing again. So we're getting at something that starts at 0 and then decreases and eventually gets to a slope of negative infinity. And then a slope again of negative infinity. Remember, this is pointing downwards, going to a slope of 0. So because of that, I'm thinking that we're looking at letter C here. Notice how it matches up. Slope of 0 to a slope of negative infinity. And then a slope of negative infinity to a slope of 0 again. So C matches with number 6. Moving on to the next one, this one has a slope of, starts at 0, goes to negative infinity. So we're looking at a piece that should look like that. I'm only seeing letter D that does that. But let's just make sure, let's keep on going. Then we have positive slopes. So we start at a great positive slope, so positive infinity, eventually going to a slope of 0. So positive infinity, eventually going to a slope of 0. Number 7 matches with letter D. Number 8 is again related to the ones that we did. Slope of 0 to a slope of positive infinity, and then a slope of negative infinity to a slope of 0. And as you're looking at that one, I think you can see that that's letter A. Slope of 0 to a slope of positive infinity, and then a slope of negative infinity to a slope of 0. Remember that these graphs here are the graphs of the derivative. So the y-coordinate is the slope. And that kind of leaves us with number 9 being linked to letter B. But it's worth us looking. Here we have a negative slope and then a point of inflection right here. So remember what I said, at a point of inflection, the second derivative should be the first derivative needs to change slope from negative to negative, or from here, negative to positive. No, positive to negative. So that matches over here. We have a point of inflection right here, and a point of inflection right here that matches with this one over here. So number 9 matches with letter B. Number 10, this is a series of questions, and what do we have? Evaluate f of 1. Well, if f of x is equal to the integral from 1 to 1 of f of t dt, sorry, that should be f of 1, f of 1. Well, just looking at that, that means that my f of 1 has got to be equal to 0. F of x is always going to be, and if you take a look at this, either increasing or decreasing, this derivative, remember, this is the graph of f prime of x, f prime of x is always positive. Therefore, f of x is always increasing. F of x is negative for which values of x? Well, if f of 1 is equal to 0, and we need to be increasing over here, that means that we have to increase to get to 0. So f of x should be negative for anything x value between 0 and 1. Are there any minimum or maximum points? Well, the graph of the derivative doesn't cross the x-axis, so there are none. And lastly, let's draw a rough sketch. Okay, so I know that we've got to get a 0 here at x equals 1. And we need to be negative on the left and positive on the right. Also, this is decreasing, so we need to be concave down throughout the entire thing. So concave down, that should give me a graph of f of x. Taking a look at number 11, this is kind of the same exercise. We know that we have point symmetry about 1, 0, so this area up here is the same as this area down here. They are the same amount of area. We got that from point symmetry again. So let's see, f of 0, well, this is again the integral from 0 to 0, so f of 0 should be equal to 0. F of 2 would be all of the areas combined, and if the area over here is the same as the area over here, then if I integrate from 0 to 2, I should get 0. F of x has a maximum value. Well, we talked about this with the last one. The derivative's going from positive to negative. Remember, this is the graph of f prime of x. Going from positive to negative, so we should have a maximum value at x equals 1. And how about a minimum value? This says f prime has a minimum value. This is the graph of f prime. So f prime has a minimum value right over here. And if this is 1 and that's 2, I think that's 3 halves. That's the minimum value. We want the maximum value, and the maximum value is at 1/2 right here. F double prime is greater than 0. Okay, so if this is a graph of f prime, f double prime would be the slope of this graph. So the slope is positive here from x between 0 and 1/2 and 3/2 to 2. The slope of this graph is negative from 1/2 to 3/2. So f double prime is less than 0 for f between 1/2 and 3/2. And then let's draw a rough sketch. So what do we figure out? We know we have a maximum value here at x equals 1. Let's draw a maximum value up here. And the area from here to here are the same. This has got to be a point of inflection. So let's draw points of inflection there. And let's just say over here. F of x, I believe, is always going to be positive. So we're looking at something that maybe looks like this. Concave up, concave down, concave up. So something that maybe looks like that. That looks a lot like a normal curve if you're in stats, but that's not really a normal curve, as you should know. So that kind of takes care of it. This is our section 6.3 to 6.4. Try to connect those values of the graph of f prime and the graph of f, and we'll see you next time.